Okay, we're back. We've been talking about periodic signals in multi-dimensions. We gave a few introductory remarks before. I also assigned you some homework problems in radon transforms and inverse radon transforms, which are used in computer tomography. So, I gave you some homework, so I'm wondering if there's any questions on the homework. I went over them last time, but there was somebody that reminded me. I won't mention his name, but his initials are David Namati. He mentioned that I didn't assign a due date for that. So let's assign a due date of Thursday for that. And then, since I did kind of go over them last time, I'm wondering if there's any questions about the homework. Have you had a chance to look at it?
I assumed it was today, so
Did you? Okay.
I didn't even look. But yeah, that's fine. I'm glad I have it done now.
Okay. Well, David got me on a technicality, so.
Nice, David. Good job.
Yeah. So I gotta be cool. Okay. Well, let's go ahead and get started then, and we will start with I don't know. This is going to be kind of. I hope you find this kind of a fun lecture. I'm going to share my screen here. And let's see. I'm going to put this up. Is this the right one? Yes. Okay. So we started talking a bit about this last time, about the concept of multidimensional periodicity. And we talked about in 2 dimensions, because that's what we can visualize. We'll do a little bit of 3-dimensional visualization later. And we talked about the idea that usually multidimensional signals are thought of as in a rectangular grid, but that need not be the case. In fact, see here we have a hexagonal grid. So we have a hexagonal packing. It's hexagonal because there's a little Yes.
We are not seeing your screen if you're trying to show it to us.
You're not seeing my screen? Okay, well, today is a day of strangeness.
There it is.
Okay, thank you for letting me know. I'd hate to go through half the lecture and you end up saying, what? What was that all about? Okay, well, we talked about the rectangular replication, which is here, which is usually what we think of. And then we said over here we had, I'm going to call this a hexagonal replication because we have kind of a hexagon that fits this packing. And this is indeed what you get by packing pennies as close together as possible. This, interestingly, is very important in information theory because information theory talks about sphere packing. The idea is you have a signal in a very high dimensional space, and then you have a region around it which corresponds to the noise. And what you want to do is you want to get a signal and the noise, and you want no ambiguity in interpretation of the signal. So this signal and the noise surrounding it better not overlap with this signal and the circular noise that goes around it. Does that make sense? And so what you want to do is you want to pack these multidimensional spheres as close as you possibly can. In fact, it's referred to as sphere packing. And that's what we're seeing here in 2 dimensions. This is the closest that you can get the pennies without overlapping. This is sphere packing, if you will, in 2 dimensions. So that's kind of interesting. Okay. And I think we mentioned about the beehive and the hexagonal replication of the beehive and how ingenious this design was, because the structure that has the most structural integrity is the circle, or if you will, a short cylinder, because it's hard to collapse the side. Imagine, for example, a triangle. And a triangle would not have the structural integrity. Can you see that if you approached a triangle in the middle of one of the sides, it would probably collapse more easily than if you had a circle? So it does turn out that the only regular polygon with equal sides that can fill up a plane is the hexagon. You can't do it with 5 sides. You can do it with 4 sides, but 4 sides isn't close to a circle. 6 sides is closer to a circle. But if you go to 7 sides, 8 sides, 9 sides, etc., you don't get the replication that you see here without overlap. So that's the ingenuity of the hexagon structure of the beehive. And this is an example of a hexagonal replication. And this is a 2-dimensional periodic function. You could think of this as a 2-dimensional periodic function where 0 is totally black and 1 is totally white. Or if you want to think in terms of bits, 0 to 255 bits if you're doing 1 byte. And this is a 2-dimensional periodic replication. And this is something that you might see on your kitchen floor. I did an interesting experiment and I wanted to share this with you. And this is something I've had a hard time publishing. It's because it doesn't fit anywhere. I decided to do the following. I took a hexagonal grid and I took some points and I wondered what would happen if there were overlapping circles, because interesting things happen when the circles begin to first overlap. So imagine these circles in a fixed hexagonal grid. So the grid is fixed, but these circles start to get bigger and bigger and bigger and bigger and bigger. And as they get bigger and bigger and bigger, they overlap circles in other regions because the centers of the circles don't change. The centers of the circles are always fixed. Okay, what did I do with my pen? Okay, David, today's your day to keep track of my pen. What did I do with it? Never mind, I found it. Okay, so the center of the circles stay exactly the same. So the centers of the circles stay here, and the centers of the circles stay here, but these circles start getting bigger and bigger and bigger. And as they begin to overlap, they give some very interesting patterns. This is more of an artsy sort of thing than it is mathematical, but I think you'll enjoy it. So here's what happens. You take these circles and you begin to enlarge the circles, as you see here. The circles get bigger and eventually they reach the point where they're kind of the replication of the pennies, right? And then you go a little bit further and you get this interesting pattern, which we'll talk about in a bit. It actually has something to do with early Christianity, believe it or not. And then we go further and we get a very interesting pattern referred to as the circle of life, which has some mystical powers according to some weird cults, but also appears in art and architecture throughout the world. And then as you go further, you begin to get things of this sort. Let me show you what I mean by this. First of all, we get the penny packing as we expand these spheres. Do you see the geometry of what's going on here? We're just taking the spheres and we're expanding them, keeping the centers of the spheres on this hexagonal array. So we get this penny packing. If we continue to increase the diameter of the circles, we get something which is called the triquetra. And it's a 3-petal pattern that is used to represent the Trinity in early Christianity. Do you see how this emerges, interestingly, as we expand the circles? So this is not expanding a circle. This is expanding a donut, if you will, that has kind of a thick skin. But if you expand it far enough, you get this so-called triquetra. And I believe it probably stood for the Trinity because you have 3 points on the petal. So I think that's interesting. Then you go further and you get something called the flower of life. And the flower of life appears in a lot of places. And it's really cool to generate. It's very easy to generate. You can generate the flower of life if you have only a compass. I don't think I can do it because of my crude drawing implements here. But the idea is you draw a circle. You draw a circle anywhere you want to. Then you choose any point. So you imagine using a circle, and the circle has a fixed diameter. So you keep your You keep your angle of your compass exactly the same, and then you draw another circle here. You put the point of the compass here and you draw another circle here. And then when you have this circle, you choose this point and you draw another circle. And if you choose this point, you draw another circle. Now, I'm probably not doing it very well. Those are terrible circles. But anyway, what happens if you keep on doing that, you get the flower of life. You should try it. It's very, very interesting. I should have bought a compass, but I'm afraid of poking little holes in my drawing screen here. Okay, so this is the flower of life. Because of its simplicity of generation, it's been found in ancient architectures all over the place. Okay, what's the matter? Okay, what's the matter? Okay, flower of life, flower of life. For example, this is one of the early works of Leonardo da Vinci. We've all heard of Leonardo da Vinci. Notice how he generates in this artistic pattern the flower of life in his early work from these expanding periodic circles. And here's another place. This was on I believe it was a rug. It looks like a rug from Turkey. And you can see the replication of the flower of life from a few hundred years ago. This is an ancient cup with the flower of life on it. And you can see the flower of life in the middle here. If you look really closely, you can see the pattern of the flower of life. So it was ubiquitous in art. It also was used in China, for example. Has anybody been to the Forbidden City in Beijing? It's yeah, it's just a majestic place, and they have all sorts of statues. And you can see here, I believe it's a dragon, and he has his foot on this ball, which is inscribed with the flower of life. So the flower of life is rather ubiquitous in culture and architecture. And of course, crop circles. Okay, you've all heard of crop circles, right? Where people come out and in their cornfield, there's these strange patterns of crushed vegetation. And people used to think, well, you know, this crushed vegetation is a result of extraterrestrial beings that came down and who did something. Now, given how I generated that, remember you draw a circle, then you put your point, then you put your compass point any place in the circle, you draw another circle, look at the two intersections of the two circles and keep on drawing them until you fill it out. You generate the pattern of life. So you can see how this would be easily generated. In fact, you can see that first of all, they generated the big circle, then they went over. And how would you generate a circle like that? If you've ever seen the crop circles, the way I've seen them generated is there's these guys that tie these big pieces of wood on their feet, and they're kind of like big shoes, and they kind of tromp along and they begin to flatten the crop. And so this would be very easy to generate using the geometry that I talked about. So anyway, these are interesting two-dimensional relationships that we can get from expanding these circles. Now, I asked the question, I thought we get such interesting results. What happened if we kept on expanding the circles? And these are heat maps of what happens. Now, I think you can see as you expand the circles and they overlap more and more and more, there's going to be a kind of a DC, a constant buildup as more and more circles add together. But we're going to remove the DC constant and only look at what's bubbling on the top. Is that okay? So we're only going to look at what's bubbling on the top. So we're going to discount all of the DC buildup. And if you do that, you get these very interesting patterns that emerge. And I think you could see also that the wider the circles, the more overlap, the higher frequency there is. Now, the high frequency in here is manifest by the detail, the kind of doily detail that you see. And so this is what happens if you keep expanding circles. So here you just had sigma, which is the radius of the circle R. If you expand all of the circles on this infinite grid to 5 times the radius, you get this result. If you expand them to 10 times the radius, 25 times the radius, and I guess I chopped off the captions down here. I'm not sure what they are, but yeah, but they keep on growing, and you get higher and higher, more detail sort of frequencies. So with this, I'm going to share with you a video to show you what happens in real time. So let's see if I can do this. Okay, launch the meeting, forgot my profile. Okay, I guess I'm going to have to reload it. All of you know that I had some problems getting the Zoom meeting started today, and apparently it erased all of the things that I had preloaded to look at. So let's go ahead and do that and reload that. This is a YouTube video, and the URL is given here. Okay, these are the Can you hear the music? Do you want to? Okay. Okay, you can see as more and more circles overlap, there's a couple of things that happen which I think are kind of interesting. The patterns get more and more interesting, don't they? In fact, they would make great wallpaper. I showed this to my wife, and she said that would make good wallpaper or a good quilt, for example, most of these patterns. But the detail gets more and more pronounced. And unfortunately, the resolution that we see here isn't high enough to capture some of that detail, but you can see interesting patterns. Now, kind of the bad thing that happens here is since we detrend it, we see kind of the evolution of the overlaps. But as soon as another circle, say far away, gets big enough to get into the field of view, boom, the DC changes and there's abrupt changes. So you can see there's abrupt changes every once in a while to the view. And those abrupt changes are when a new big circle interferes with the main circle. So we get kind of a strobe effect here, if you will, with the changing. Okay, I want to play for you something. This is good. Okay, listen to the music here. This is called I forget the name, it's a glissando, but it's a tone that sounds like it's always decreasing. I don't know if you've ever heard it. You've heard of optical illusions. This is an audio illusion. And it sounds like the tone is always decreasing, but it never decreases and it stays exactly the same. I put it in for the audio background here. Okay, it didn't go on for very long, but it's interesting.
I don't hear anything, Dr. Marks.
Oh, you don't hear anything?
No.
Okay, you're not hearing anything. Okay, well, okay. So apparently my screen sharing isn't the same as the audio sharing. Did you hear the music before?
At the very beginning, yeah.
Okay, I wonder what happened.
Now we listen.
Interesting, the background there, the drumming part is supposed to be also an audio illusion. It gives you the sense that the beat is speeding up, but it really isn't. I didn't find that as convincing as the glissando, which always sounded like it was raising in pitch, but nevertheless, it's kind of interesting. Okay, so I think it's running backwards now. I decided to run it forwards, and then I was going to run it backwards. Okay, so isn't that interesting? These circles just get bigger and bigger and bigger, and if they're detrended, you get these fantastic, I think, very interesting doily patterns. So you wonder what's going on here. So we see a few screenshots here of what goes on as this overlapping circles get larger and larger and larger. So I wondered what would happen if instead of an expanding circle, you did an expanding box. One of the things that I proved using the mathematics that I'm about to present to you is that when you have expanding circles, you never, ever, ever see a repeating pattern. That every pattern is unique, and these unique patterns will continue forever. It's a very interesting consequence. And not so if you talk about an expanding circle or expanding an expanding rectangle. So you have a rectangle on a hexagonal grid, and that rectangle gets larger and larger. And also on the hexagonal grid, you have the rectangle that gets larger and larger. And you look at the overlap, and you detrend them. So this doesn't work out. This doesn't work out to be as cool. But let me show you. Let me show you what it is. In fact, with this one, there's a periodic replication. You literally see a periodic replication temporally, not spatially. Spatially, it's periodic, but temporally, as time goes on, you see a repeat of what goes on. So let's see if we can get this one going. It's actually kind of boring if you talk about a rectangle. I guess I got to hit the play button, right? I don't know if you can see it, but there is a periodic replication. The patterns repeat themselves when they're detrended. And the patterns, frankly, are not very interesting, are they? There's no introduction of higher dimensions. Or there's no replication of higher frequencies that is interesting at all. So these are expanding rectangles on a hexagonal grid that's infinite, and it's not very exciting. So the last one that I want to show you here is this one, which instead of it expanding circles, we did expanding cones. Now, the good thing about cones is they expand as they begin to interfere with the main tile, if you will. There isn't an abrupt change, there's a gradual change. So we won't see the strobe sort of effects that we saw with the pillbox, that we saw with the expanding rectangles. So this is a cone, and the height of the cone stays the same and it just begins to spread out in a circular fashion. And it does this all along the hexagonal grid. And these are some of the patterns that we see. Up in the upper left here, you can see the beginning of the heat map of really tiny pointy cones, right? And then the cones get larger and they begin to overlap and they do interesting things like just like these circular pillboxes as they get bigger and bigger and bigger and bigger. But they are more interesting. And I want to show you a video, and that's the last video we have, so you don't have to go pop popcorn. The videos are about over. It's too late for popcorn. Now this one is displayed in a little bit more interesting manner, as we'll see. You can see not only the heat map, but you can see a three-dimensional heat map of what happens. And it's just fascinating. I think it's fascinating to watch as these cones begin to expand further and further and further. And notice everything is gradual. There's no abrupt changes at all. It's just a gradual change. Again, as these cones expand, the DC buildup, the background buildup is going to be ever increasing. So we have, if you will, detrended it by removing the DC buildup and only looking at the top of the periodic function. In truth, this periodic function rests on a very high bias. This is also something you can show that never repeats. There is never a repeating pattern here. Every pattern is going to be unique from now until infinity. So I see Glauco is getting out of the sun. Okay, I think I'm running it backwards now. I ran it until the maximum number of expansion, and then I began to run it backwards. So I thought this was interesting. This displays two-dimensional periodicity on a hexagonal grid generated in a very interesting fashion. So very cool. Okay, so those are the pictures that I have and the movies that I wanted to show today. I hope you found them entertaining. Let me tell you, it took a long time to generate them. Okay, let's go ahead and move on. I wanted to go now into three-dimensional periodicity and how they occur in nature. We saw sphere packing, for example, in 2 dimensions where we put pennies as close as possible together. Three-dimensional sphere packing occurs when you try to put bowling balls, or I think in this case it's cannonballs, together, spheres together in the closest possible fashion. You get a periodic replication. And if you're into communications or information theory and you want to maximize the sphere packing in 3 dimensions, this is the geometry that would result in these cannonballs. So we have a 3-dimensional periodicity here. Explaining again, just illustrating how 3-dimensional periodic objects occur in nature naturally. There is also the area of 3-dimensional periodicity in crystals. And we talked about this last time. And the people in crystals study these a lot. And there's a question of what sort of objects can you put together? And we're eventually going to call these tiles, because in 2 dimensions, putting these tiles together, we'll be able to tile your kitchen without overlap. So what are the shapes of the tiles? This is the equivalent problem except in 3 dimension. We're doing a 3-dimensional tile, if you will. So we want to be able to replicate this, this structure and stick them together, put them together in a fashion so that they fill up a 3-dimensional space without any gaps. Notice that doesn't happen with a bowling ball, right? With a bowling ball, there's gaps between the balls. So a spherical object would not work here because it would leave gaps. The tiles that we're talking about cannot leave gaps. So clearly a cube, the cube that we have down here, this cube is not going to be able to, or is going to be able to be duplicated and stacked so that you don't get any gaps in the replication. And these other things, which are people that do crystals talk about, what, an octahedron is also interesting in that it can replicate and fill up a 3D space without gaps. And these two over here are not as obvious to me, but they're claimed on the internet as filling up a 3-dimensional space, and everything we read on the internet is true. So this must fill up a 3-dimensional space. So this is an example of a 3-dimensional periodicity of a so-called tile that can fill up a 3-dimensional space. Okay, any questions on that? That was just basic introduction material. It's not that deep or heavy of a subject, but it's still very, I don't know, I think it was very interesting and might give you a better idea of what's going on. We want to talk now about Fourier series. We know in 1 dimension that if we have a periodic signal, then we can represent it as a Fourier series. What's the equivalent of a Fourier series in 2 dimensions, 3 dimensions, and higher? Well, one of the things that we have to do in a 1-dimensional periodic signal is identify the period. And the period is the shortest length where you can take a cookie cutter, if you will, and take a period and replicate that period down the time axis in order to generate the periodic signal. So how do we extend that to a 2D signal like this hexagonal grid here? How do we characterize it? In 1 dimension, we characterize it with the period t. What do we need to characterize it with in these in higher dimensions? And we're going to look at the 2-dimensional case, and I think you'll see it generalizes very nicely to higher dimensions without much problem. The way we do it is follows. We look at the center points of the replications. So if you will, here is a center point of the replication, here is a center point, here is a center point, and you can see these are center points of a tile. So if we could talk about a periodic signal as being, you know, putting a smiley face here, putting this smiley face here, and putting a smiley face here, and we put the smiley faces all over the places, and we would have a 2-dimensional periodic signal. Does that make sense? So these are the centers of the replications of the periodicity. There is something here referred to as a periodicity vector. Now, a periodicity vector takes the place of the period, the capital T, the period in the 1-dimensional case. And as you might expect, we're going to need 2 scalars, or I'm sorry, not 2 scalars, but 2 vectors in 2 dimensions in order to characterize the dimensionality. And the way we do this is that we look at this one value here, and we're going to call that P1, and the vector here, which is P2. And once we do this, this allows us to label all of the points in the plane. as multiples of P1 and P2. For example, this point here, 1, 1, that means that's 1 times P1 plus 1 times P2. So that's this point. This point here would be twice P1 minus P2. Look at that for a second and see if you agree with that. Every point in the plane can be characterized by an integer pair, which is the weighting of each one of the individuals. So 1, 0, for example, would be 1 times P1 plus 0 times P2. Over here, this is nothing more than minus P1. Plus 0 times P2. Is that okay? Then by doing that, every one of these points has integer values. Each one of these points has integer values, which is assigned to it. And these integer values correspond to the weighting of the P1 and the P2 to give us this point. I think you can see this can be generalized to higher dimensions also, where we would have periodicity vectors. And in general, we would have, if we had n vectors, then each one of these periodicity vectors would be a vector of length n. So does that make sense? That's the replication that's the replication of the periodicity.
Dr. Marks?
Now from the periodicity, we form something called the periodicity matrix, which is P. And this is just stacking up the periodicity vectors side by side, P1, P2. If we're in 2 dimensions, we stop here, right? That's P1, P2. So in our example, P is equal to 1, 1, which is, it's not really clear here, but this is 1 here. So 1, 1 would be 1 over and 1 up, right? So this is P1. And 2, 0 would be going over here to 2. And that would be the second periodicity vector. Is that okay? So we're taking the P1. The P1 is equal to 1, 1. And we're taking the P2, which is 2 sub 0, and we're simply concatenating them, laying them side by side in this animal called the periodicity matrix. And this periodicity matrix is the fundamental identity, if you will, of periodicity, and replaces the idea of a period in 1 dimension. And a period, all we need is a period here if we have t. And notice the 1-dimensional thing is kind of a degenerate of this. Here we need 2 2-dimensional vectors. In 3D, we need 3 3-dimensional vectors. In 1 dimension, we would need 1 1-dimensional vector, right? 1 1-dimensional vector, and that 1 1-dimensional vector is the period t. So therefore, we can see that it extends very nicely, intuitively, down to the scalar example. So the periodicity matrix, again, describes this. Now, here's something interesting. Well, let's see. Maybe I'll get to that in a second. No, I don't think I will. Okay. Can anybody tell me what the determinant of P is? Now, this is acting on the point that you have a vector here, and you have a vector here. That's P1 and that's P2. Do you know what the determinant of P gives you? This is very interesting. It gives you the area of the parallelogram that is formed by those two vectors? The magnitude of the determinant. So again, if you have a P1 and a P2 and you make the periodicity matrix, then the determinant, the magnitude of the determinant of the periodicity matrix is the corresponding area of the defined parallelogram. Very interesting result. So what's the determinant of this P? You can do this in your head, right?
Yeah, it's 2.
You can do this in your head, right? What is it? 2. That's right. Adam was too lazy to turn on his audio, so he held up 2 fingers, which is fine, which is fine. The determinant is 2. Now let's look down here. Let's look at the area of this parallelogram. Is the area of that parallelogram 2? It is. The area of that parallelogram is 2. The way you can do it is take this little triangle here and notice that that fills in the missing triangle here, and you get a square, or you get a rectangle of 2 by 1, don't you? So yeah, therefore the determinant of this periodicity matrix is equal to the area of the parallelogram.
Dr. Marks? Would that be the size of the tile you're replicating also?
Now here's something that's interesting. The periodicity matrix for a given
I don't think he's
replication
listening.
geometry is not
They're not
Yeah.
listening. Yeah.
We just went through this example of, let's
Dr.
see,
Marks.
when we went to, yeah, I guess 1, well, no, this one's 1 minus 1, and this one is 2, 0. I think I made him, uh-oh. What's the matter?
You can't hear us.
Uh-oh, can you hear me?
You can't hear us.
Okay, I can't hear you. Okay, try now.
Can you hear us now?
Yes, I can.
Okay.
Okay, you wanted to did you want to interrupt me, or were you just like
Yeah, I had a question about the last part there with the area.
Oh yeah, okay, great.
Would the area also be the area of the tile you're replicating, sort of?
Yes, in fact, we're going to get into that. That is that's a non-causal question. Okay, so that is something that we're going to get to. But yeah, very good insight. Very good insight. Okay, so here we have for the same periodicity, notice the periodicity points are the same in 1, 2, 3, and 4, right? But what I've done here is I have characterized them by different periodicity matrices or different periodicity vectors. And what this does is it's going to change the integer indices on all of the points. So the integer indices must refer back to how you initially label the 2-dimensional vectors, right? The periodicity vectors. So here is a possible periodicity. Here is a possible periodicity. For example, here, this point would be 1, 1, right? What would be 1, 1 here? This point, right? This point would be 1, 1. According to these periodicity vectors. Over here, the point 1, 1 would be off screen. It'd be way up here. So we see that the indices of the labels are changed. But all of these are possible periodicity vectors with different periodicity matrices that describe exactly the same replication on the T1, T2 domain. Isn't that interesting? What do you think they all have in common? the corresponding periodicity matrices.
Same determinant?
Same determinant, because this area, look, this is the area. Think of this as a tile, okay? You have this kind of diamond-shaped tile that you go and you're tiling your bathroom floor with. And you replicate this all over the place to tile your floor. You can also think of this as a tile that you use to tile your floor. Wouldn't you expect that the size of this tile would be the same as the size of this tile? Well, maybe you would, maybe you wouldn't. But let's, in fact, let's verify this. Let's look at the periodicity matrices for these corresponding results. This one is, on the left here, is 1, 1, right? 1, 1, and then minus 1, 1. Is that okay? This is the P1 here, and this is the P2. So do you agree that that's 1, 1, minus 1, 1, right? So that's the periodicity matrix for this one. Over here, this is going to be P1, and this is going to be P2. And that's going to be 2, 0, right? Going over 2, 0. I haven't labeled my axes very well, but that's 1 and that's 2. So it's 2, 0, and then minus 1, 1.
Yeah, one thing that stands out to me is that if we choose an orientation such as like first, bottom, and then left, we can say there's, yeah, every point, every dot is on that position for one tile, and the so there's one tile per point, and the number of tiles and the area, the total area, does not change.
The total area does not change. And David is right. For example, there's 1 point for every tile. So for this tile, there's a point. For this tile up here, there's this point. For this tile, there's this point. So we can do a one-to-one correspondence with the number of points and the number of tiles, is what David was mentioning, which is true. So we have down here 1, 1 and 1, 2. I'm sorry, 0, 2, 1, 1 and 0, 2. This would also be a periodicity matrix for this replication. The replications, again, in all cases are identical, or even get kind of weird over here and go to 2, 0 and 3, 1. That's also a periodicity matrix. Now here you're going to have a long, skinny parallelogram, right? But if David is right, then the magnitude of the determinants of all of these periodicity matrices are going to be the same. In other words, equal to the area of the tile. Are they the same? What's the determinant here?
2.
2. What's the period here, or the determinant here?
2.
2. That's right. What's the determinant here?
2.
2. Okay, this is getting boring, right? And what's the determinant here? It's also equal to 2. So the determinants of all of the periodicity matrices, even though the structure of the periodicity matrix can change quite a bit, they're all equally valid, by the way. There's not one that stands out above the other ones, except that you would kind of like there to be simplicity. Like, I don't think I would use this as a periodicity matrix because those numbers are getting too big when I can use smaller numbers. But that's just something which is aesthetic. But all of them are equally valid. But all of them are going to have areas exactly the same. The areas of the corresponding parallelograms. One of the things that we got to make sure of is that, well, we can talk about the determinant of P. That's equal kind of, I call this capital T. I don't know if that's the best of notations, but that's the area of the parallelogram. And we must assure ourselves that, that P is not singular. What happens if P is singular? We get pretty boring periodicity. We really don't get periodicity. We get, say, this is P1. And in 2 dimensions, if the determinant is equal to 0, that means that the 2 periodicity vectors are collinear, aren't they? So they're pointed in the same way. And if we had P1 is equal to P2, you know, what we would get is something like, if we were replicating, well, say we were replicating a circle. If we had this periodicity matrix, we would replicate it in a hexagonal fashion. If, on the other hand, our periodicity vector was singular, we would be replicating it just in 1 dimension, wouldn't we? We would be replicating it just in 1 dimension. So therefore, in order to have true periodicity, we must make sure that the P matrix is not singular, does not have a 0 determinant. Otherwise, you're not going to fill up the entire plane. You're not going to fill up the entire plane, are you? So here is the definition of periodicity. Down here at the bottom, you can see a periodic replication of crosses here. As usual, we consider values inside the cross is equal to 1, values external to the cross is equal to 0. And we do this in order to be able to represent kind of the 3-dimensional structure of the 2-dimensional replication in just 2 dimensions by a drawing. Well, first of all, the definition of periodicity means that S sub u is equal to S of u minus P1. Well, this is P1. So what does that mean? This means if we take, by the way, we're in, this should probably be relabeled as U1, U2, because I'm in the frequency domain here. If we take the entire function and we shift the entire function, a periodicity vector of P1, we get exactly the same thing, right? If we shift the entire 2-dimensional function, we shift it to P1 and we get exactly the same thing. But that's not enough, because if we just did it in 1 dimension, we could do a 1-dimensional replication. And if we shifted this in terms of just P1, we would still get a replication, and we would just have a 1-dimensional periodicity, but not a 2-dimensional periodicity. So we also have to do it in the other dimension. We also have to do it in the other dimension. So we have to also take this same 2-dimensional periodicity, and if we shifted it to the right by an amount P2, we would get exactly the same thing. So we have 2 tests in 2 dimensions. So in 2 dimensions, we only have to go up this far. In 2 dimensions, we only need to go up this far. Now this is equivalent to saying, if we take the original signal S of S and U, and then let's see, we shift it by P sub M. What does P sub M means? Well, P sub M, P times M, is the periodicity matrix times a vector of integers. So M, for example, is equal to a vector of integers. It could be equal to 1, 4. It could be equal to, 1052. Okay, but it has to be integers. If you remember, we were able to label all of these points in accordance to integers. Like this point would be 1, 0, right? And this point down here would be 0, 1. Do you remember we could label all of the points in the periodic replication? What would this point be? It would be 1, 1, wouldn't it? And this point, I believe, would be, help me out here, 1, yeah, 1 minus 1, right? Whereas the one over here would be equal to 0 minus 1. Now we can think of all of these integers as a vector. For example, this would correspond to a vector of 1, 1. Is that okay? That would correspond to the vector 1, 1. And this would correspond to the vector 0, minus 1. And if this periodicity extends forever and ever and ever, then no matter what, no matter how big of an integer you put on there, there's going to be a point in that replication which is assigned to 1,000. 1,000 times P1 plus 52 times P2. So suppose we took a point up here, and I'm just going to exaggerate here. Say this is M is equal to 50-50. And so here we're going to have, if you will, a cross. That's supposed to be a cross, if you will. So this definition of periodicity says if we take this original two-dimensional function and we shift it to be centered, the new origin, this is the old origin, this is the new origin. If we shift it to be centered at the cross here, we're going to get exactly the same thing. So that's how we interpret this. And again, M must be a vector of integers. And this is the definition of periodicity in higher dimensions. Now, we understand it very straightforwardly for 2 dimensions. This also extends to higher dimensions. I think you can see that the higher dimensions would also be applicable here. That's the kind of cool thing about multidimensional periodicity, is that you can, or multidimensional signals in general, is you can kind of visualize things in 2 dimensions, maybe 3 dimensions, and then extend it to higher dimensions. So you can see that idea extending to higher dimensions. So this is all well and good. Now, let's talk about tiles in our last few minutes together. Let's see, you know what, this would be a good place to literally end the lecture, because I want to talk about tiles, and we'll talk about tiles the next time we meet. Next time we meet, we'll go over the assigned homework problems. They'll be due at midnight on Thursday. And so, any questions on the lecture? Okay, well, thank you all. I hope you're having as much fun as I do. I'm hoping you're having as much fun as I do, as I have. I hope you're having as much fun as I am having. I think that's the proper saying. Okay, any questions at all? Okay, that's great.